Welcome to our Fluid Mechanical Dissection, Resistance Bike Trainer Edition. So what is our exercise bike? You mount your bike to the front bar over here so that it connects to the entire thing. Your wheel is going to connect to this cylinder here that once you start biking, it rotates the impeller that's inside of this casing immersed in oil. So that oil is going to add resistance with the impeller together to give you a good workout.
The assumptions we'll be making in this analysis is that there will be a uniform pressure distribution at a radius, there'll be neglecting viscous effect, there'll be incompressible flow, and there is no leaks or drips.
When we look at the Reynolds number and calculate it out using a speed of approximately 110 RPM, which corresponds to approximately 9 miles per hour on the average bicycle, we can combine that with our diameter of the impeller and the density and viscosity of oil to get our final Reynolds number, which is really, really high. So this validates our assumption to ignore viscous effects because our high Reynolds number tells us that the fluid mechanics are big enough and fast enough to be dominated by the fluid inertia.
Oil is used inside of these systems for its relatively low density. It creates that resistance for the bike trainer. If we use something like air, which has a very, very low density in comparison, we wouldn't get that resistance. Water could also be used, but water has a higher density than the oil, so it will have a little bit more viscous effects. Oil is used for its lubricating properties, so it's the best fluid to use. Looking at the pressure distribution, we can see that there's a high pressure region on the outer edges of the impeller and a low pressure region on the inside. This is described by this equation, which relates the radius to the pressure of the fluid inside of the impeller. We can also see from these arrows that they are different magnitudes. These velocities are described by Euler equation for the pressure distribution normal to a fluid streamline and in viscid flow.
Our bike trainer device operates similarly to a torque converter in the way that it manipulates the angular momentum of the rotating fluid in the system. The torque converter transmits power from the engine to the transmission via the fluid being passed between the impeller in the orange and the turbine in the pink. When the impeller spins faster than the turbine, the fluid flows poloidally, with more momentum being transferred to the turbine at the highest pressure region at the outer edges of the system. As a result, there is a backdriving torque present on the impeller. In our bike trainer, the quote-unquote turbine, which is actually the volute casing cap, is completely stationary, so the system will not reach equilibrium at high speed. Instead, as the impeller is spun faster by the bike wheel, there will be a higher backdriving torque resisting the motion. The graph on the left shows a typical performance curve of a torque converter. The speed ratio represents the difference between the impeller and the turbine speeds, and the torque ratio shows the difference in torque input from the impeller to the torque output. So the faster the impeller spins than the turbine, the greater the torque difference. Since our device has its turbine or casing cap stationary at all times, we can say that the torque difference represents the backdriving torque resisting the bike wheel. This explains why the bike experiences resistance at higher speeds, simulating the real-life conditions that a bike rider would experience on a road. The impeller has 6 vanes that do work on the fluid, while the casing cap has 5. Cap vanes also oppose the direction of the impeller vanes, which facilitates the fluid being transferred back to the impeller. The impeller vanes are much wider than the cap vanes because they are generating the angular momentum in the fluid as the impeller spins and can move the fluid easier with a greater surface area. Since the vanes on the cap act to transfer momentum back to the impeller, they do not need to be as wide or as numerous as the impeller vanes. If there were more or wider vanes on the cap, the resistance generated would be much thicker than what is targeted by the system to simulate road conditions. So if this device were to be larger, the pressure at the outer edge would be much greater and the fluid would move much faster. This would also increase the resistance to the impeller and require a more robust design.
The goal of the design is to dissipate energy that the user generates during riding as heat with the addition of fins to the outside casing. Fins are extensions on exterior surfaces of objects that increase the rate of heat transfer to or from the object by increasing convection. This is achieved by increasing the surface area of the body, which in turn increases the rate of heat transfer. This would be the most optimal way of increasing the rate of heat dissipation, as the alternative solutions are expensive, difficult, or generally just impractical. We would have to increase the heat transfer coefficient or the temperature gradient. Changing the shape of the body is more convenient. The thermal efficiency of the machine is 0. The machine is designed such that the fins can dissipate energy quickly enough so as to prevent the trainer from getting too hot. It is intended that most of the energy that a user puts in is dissipated as heat through fins instead of as sound or as turbulence.
Our fluid machine is very similar to a centrifugal pump with no inlet or outlet in the way that the impeller rotates the fluid, and we can make this device a pump by adding an inlet that lines up with the center of the impeller and an outlet. The rotating impeller creates a region of low pressure at the eye, which draws in more fluid, and the limitation of this, however, is that the intake pressure must never be lower than the vapor pressure of the fluid, because if this happens, the fluid will cavitate and cause damage to the pump components. The rotating impeller accelerates the fluid centrifugally, and an increase in the cross-sectional area causes the fluid to decelerate since the flow rate must remain constant, giving us a region of high pressure and low kinetic energy at the outlet and high kinetic energy and low pressure at the inlet. A limitation in our machine is that there is a uniform cross-sectional area in our volute casing, whereas most centrifugal pump volute casings are uniformly increasing in cross-sectional area, which minimizes the head of our homemade pump.